half-wave rectifier, essentially a controllable half-wave rectifier, is what we looked at in the last session. And so what we're going to do is we're going to continue on with the SCR, and I'm going to show you how the full wave rectifier looks using an SCR. Okay, so just by way of review, I'm going to show you a review circuit first, and then we're going to do the full wave. So the half wave looked like this. Here we had an AC source. We came in like this. We had our load. Then we had our SCR. Okay, and over here was the gate. Anode, cathode. And then we came back, and that went back to the source. Now, also attached to this was the load part, right? Load. And here was the trigger circuit. And the main components of the trigger circuit were, we had to have a resistance, and then we needed to have a diode, gate protection diode. So this was gate protection diode. And that was there, the purpose of this diode is to prevent when the AC comes into the negative part of the alternation and it starts to push from this side back, the cathode to anode is able to block perfectly. But remember, the reverse voltage rating of the gate is very low. So without this diode, it will actually allow too much current to flow through and it will destroy the SCR. So this is necessary. This gate protection diode is necessary mainly because the AC, when it reverses, will come and it will push back against it and will try and push reverse current through the gate. Now, I want to review the formula, which was for finding the load voltage. The formula that we used for finding the average voltage, E average, which is the same as the DC load voltage. The formula that we used looked like this. It was E average is equal to E of the peak. As we remember, we have an AC waveform here, so you've got your line values. Let's say this was 120 volts. The peak of this would be about 170. So that's part of this formula. The peak times 1 plus the cosine of the firing angle divided by 2 pi. Okay, so that's a formula, a review formula that you need to look at. Now, the other thing that came into play was there were times where we needed to know what the instantaneous voltage was in order to properly calculate firing angles. And so I'm going to also give you that by way of review. E instantaneous is equal to, and we're looking at, let me see, E instantaneous is equal to E peak times the sine of whatever angle it is that we're talking about. So if you're looking for the instantaneous value of voltage at 30 degrees, you'll find that the sine at that point is actually 0.5 or 50%. If you're looking for the instantaneous value at 60 degrees, well, you look for the sine of 60 degrees and you'll find that it's 0.866 or 86.6%. So that's how we find our instantaneous values. Okay, those are important to note. Now, when we move to, we're going to now talk about the full wave rectifier. How do we make a full wave rectifier? And so what I'm going to do is I'm just going to clean this out of the way, and we're going to start by looking at the full wave rectifier using an SCR. Now, I'm going to start by showing you the load and the SCR. And there's the gate right there. Gate. Anode, cathode. I'm going to change that up. I'm going to make that the gate. Now I know that this is going to have to be fed from over here, so I'm gonna just make a couple lines over that way. Now, in parallel to this, we're also going to have to look at a trigger circuit. And so I'm going to start, there's the resistor, and we're building a trigger circuit here, and I'm going to take that and I'm going to take it straight into the gate. Now, why did I not put a gate protection diode in? Why did I not use a gate protection diode? Let's talk about this for a minute. Well, what does that gate protection diode do that we put in the previous circuit? It prevents current from going the wrong way, backward through the gate. And that's what happens when you feed it with an AC circuit. So we look at it, we go, well, maybe there's something different going on here. Where is this actually coming from? Let me just show you. This is a bridge rectifier. This is the positive terminal, the negative terminal, and this is my AC input on these two corners. So there's our connections. Now I'm going to take this and I'm going to go like this. And now here is my AC supply. So this is AC. Now, the interesting thing is that this can be the same voltage. I can make this 120 volts AC. And how many volts DC will this give me over here? Average voltage. Now, this is really, there's 4 diodes inside of this, okay? D1, D2, D3, D4. So there's diodes in there, but those are not part really of what's going on here. This is the SCR controlling what's essentially an, it's going to be actually an average voltage. It's a DC voltage. So because this line is always negative, it means that as it should, the current will only flow from the anode to the cathode, and when I get a trigger pulse, it'll go from the gate to the cathode. And because this is always negative, it never turns around and tries to push back, and so we don't need a diode, okay? So in this circuit, now our output waveform is going to look a little bit different. I'm just going to give you a reminder. What did the waveform look like in the half wave? Half wave. Okay, so our possible outputs looked like this. At 0 degrees, our output looked like this. It looked like a full, this is like what the load would see, okay? There's the load at triggering at 0 degrees. What happened if we trigger at 30 degrees? Well, then it would look like this. It would go, basically it would block. Then remember, this is load voltage we're looking at here. And that's what the load would look like at 30 degrees. Let's go ahead and look at 60 degrees. And so we go, there's our 60 degrees. Now we're going to block all the way over to here. Then it's going to go up. There's our 60 degrees. And so you can see that the amount of voltage, remember, if these were ice blocks and you were melting them down, the voltage would be getting lower and lower. And let me show you the last one at 90 degrees. And it looks like this. Basically, we block for 90 degrees, turns on, and there it is right there. And remember, second alternation always blocks. So there you see the half wave rectifier, 0 degree firing, 30 degree firing, 60 degree firing, and 90 degree firing. This is essentially now a quarter wave rectifier because we only have 1/4 of what the full, if we had 2 complete ripples, this is only 1/4 of that. Now, Now though, what does the output waveform? I'm going to call this the output of the bridge. Okay, the output of the bridge. Well, let me draw it for you. It looks like this. I'm going to draw 2 cycles for you actually so you can see a little bit of length to it. That's 2 cycles of the output from the bridge. So that means we get an alternation from this, one alternation, and then we get the second alternation, because what these diodes do is they flip over this negative alternation and feed it in as though it was positive. So we get, this is 2 cycles here, and we see actually 4 ripples, so 2 ripples per cycle. Now, if we were to control this with an SCR, so now we go and we look and we go, oh, we have an SCR in here. So what voltage will the load possibly see? So here's what we could do with the load. I'm just going to draw one complete cycle of the load for you so you can see what would happen. Using a resistance only, which is what I have here, here's my earliest firing angle would be right here. This would be firing at 0 degrees. 0 degrees firing. This is load. This is the load we're looking at. And what would my very latest firing angle be? Well, resistance only, it's going to be 90 degrees. So here's what the waveform would actually look like if I had 90-degree firing. Okay, so it would block for 90 degrees. This would be the firing angle, 90-degree firing angle. Turn on, it would have voltage until 180. Then block again for another 90 degrees. Turn on and conduct down there. And so what we see is now what we got with 90-degree with a 90-degree firing angle here was just one large shark fin. What we have here is 2 large shark fins now, and this would be at 90-degree firing. So we can now vary the voltage from this amount up to this amount. And if we were to take this value and compare it to the line voltage, this voltage here would be E line times 0.9. That's how much voltage we would literally get from these 2 full alternations triggering at 0 degrees. And of course, if we trigger at 0 degrees, you got to realize that's the same as if we had diodes in the circuit, right? Now, because it's an SCR, we can actually dial it down. How much voltage would I have? What would my voltage be for the load in this case? Well, if I've taken away exactly half of the voltage, then this would really look, tell me, this is just an interesting side question for you. Voltage-wise, what is the difference between this or this? Okay, now just imagine this cut in half. If I took these 2 and popped them into here, exactly the same amount of voltage. And so we know that a single phase half wave is E line times 0.45. So guess what? A full wave rectifier triggering at 90 degrees, this value is also E line times 0.45. Okay, and this is using the resistance only triggering circuit. Now, one of the important things that we come up with is once we know we've seen the circuit and we know that we can now delay our firing angle to any sort of variable level. We'll put a variable resistor in here. We can play with it. And what we're going to discover is that there will be varying levels of load voltage. So what I'm going to do is I'm going to move this diagram. And what I want to show you next is what is the formula? What is the formula to determine the amount of load voltage? Now, the load voltage is always the average voltage, right? E average is equal to, well, you need to know what the peak is. And remember, the peak will actually be exactly the same as it was if you were just supplying it from 120 volts AC onto one SCR. In this case, you go through a bridge, but that doesn't diminish the overall height of the waveform. It just makes all the waveforms on the positive side of the line now. So you would still look at it as, for instance, in the example I was using, this would still be 170 volts times 1 plus the cosine of the firing angle. Now, up to this point, it looks like the exact same formula, doesn't it? And yes, it is, but seeing as we're now dealing with 2 alternations instead of just 1, we only divide by pi, not 2 pi. And so this formula is specific to the full wave rectifier. And the formula that I showed you earlier with 2 pi here is specific to the half wave rectifier. Okay, so just make sure you have that distinction. Okay, this one is the full wave. Full wave. And if it's 2 pi, then it's the half wave. Other than that, the formula is completely identical. And it makes sense. If what I just showed you over here, if you have twice as many ripples, you're going to need to have twice as much voltage. That's what's going to happen. So now we have that. Let me just show you an example of how this will look. We'll work it out with a circuit. So I am going to do an example, and this is how it actually looks, all right? I'm going to put the circuit just below the formula here, and then we can work with it in that way. Now, I'm going to start with a line of 160 volts AC. Okay, 160 volts AC, and I'm going to move across. And what I'm going to do right away is I'm going to come in, and I'm going to put a bridge rectifier. Plus, sorry, that's going to be the AC point there. So AC, AC, and I'm going to make this positive and this negative. So what I want to do is I'm going to go from these corners now. I'm going to take this line up. Remember, this is positive. I'm going to take this line over here. This is negative. And here we go. And we're going to move in. Now remember, I want the anode of the SCR to be positive. So I'm going to put the load here, first of all. This is my load right there. And I want to put the SCR right here with the anode positive. I'm going to draw the A part of that. Now I'm going to finish off the K part of that. And there is my cathode on the negative terminal. Now over here, we're going to need something. Now what I've done in this example, just to show you how this is going to work, talk about it a little bit. It looks like we have right here a 1000 ohm resistor, and it's just a fixed resistor. And then what we have following that is a 0 to 20 k ohm variable resistor right here. Okay, so that's like this. Now, got my gate down here. I'm feeding this from essentially now it's a DC output. I don't need a gate protection diode. And so I'm just going to hook that to the gate. Now, I do want to stop here for a moment and just ask you a question. If I did put a gate protection diode in, would the circuit still work, or would it really affect the circuit at all? And the answer is it would make very little difference. The current would still flow through it forward as it should. It would never have to block anything because there's nothing coming back against it. So the only real difference is you would have an additional 0.7 of a volt of barrier voltage. And so it's unnecessary to have it there, but at the same time, the circuit would still work if it was there. Just a slight difference in your values, not much. Okay, so here we have the circuit then, and I'm going to give you the information about the actual SCR, and it looks like this. The voltage of the gate is 3 volts. And the current, IGT, so the current that it takes to actually trigger this is 80 milliamps, okay? 80 milliamps. And I think that's about all we need. We can carry on now and answer some questions about this. First of all, the first question that comes up is, what is the earliest possible firing angle? Now, to look at the firing angle in this circuit, what we need to realize is that's going to be determined by our settings in the trigger circuit. And this is going to control how fast or slow the current flows, how fast the current rises as the waveform coming from the source is rising. How fast is the current going to rise, and at what point are we going to get 80 milliamps to trigger the gate? So let me tell you, let's look at it this way. The earliest firing angle will be when we have the least amount of resistance. And so what we want to do is we want to turn this to 0. This rheostat is completely at 0. And at that point, we still have 1,000 ohms in our trigger circuit. So that's actually the minimum amount of resistance. And this will determine our earliest possible firing angle. And let's go ahead and see what it is. Let's work it out. So how do I find what that firing angle will be? So I'm going to start with this. We know how much current we need, and we know how many ohms we have. So what is the value that we come up with using R and IR? Well, what it's going to be is going to be voltage. Okay, so we're going to determine a voltage. And so I'm going to grab a calculator, and just to make sure that we stay on the right track with this, and I'm going to go 1,000 ohms times 0.08 of an amp. And that voltage is 80 volts. 80 volts. Now, with 80 volts, we would say, is that the instantaneous voltage? And the answer is no. That's actually the voltage that we get here. You know, that's the voltage that it's risen to. So remember, the waveform's going like this. The waveform's going up, and it's going to go down. How high is it going to be at the peak? Well, it'll be 160 times this peak up here will be 226.3 volts. That's the highest point. So if I look at it and I say, well, 80 milliamps and 1,000 ohms means that I have 80 volts, there's one more thing we have to consider. So that means if I apply 80 volts from here to the cathode, I get 80 milliamps? And the answer is not quite, because there is this 3-volt barrier voltage that I have to overcome. So that means I have to go 80 volts, which is really E of the resistor, plus the 3 volts, which is E of the barrier. And if you add those two together, that equals 83 volts. And that is E instantaneous, okay? So now we can say, okay, where does 83 volts instantaneous? It's gonna be around here somewhere, okay? So I say, if that's 226, you know, 83 volts is around here. And now we need to use our instantaneous voltage formula. And what it says is that 83 volts is equal to 226.3 times the sine of the angle. Now, we don't know the angle, so that means we're going to have to solve this. We're going to have to solve this out to find what the sine of the angle is. So we're going to divide this by 226.3, and we're going to divide this by 226.3, and let's see where we go. 83 divide 226.3 equals the sine of the angle. And what I come up with is 0.3668. So now if I go inverse sine 0.3668, I come up with an angle of 21.5 degrees. 21.5 degrees. And so that means that my firing angle, the SCR here, is actually firing at 21.5 degrees based on that 1,000 ohms. And that's my earliest possible firing angle. I cannot reduce that any less without actually changing that resistor. So there we have it, 21.5 degrees, the earliest. Now, what would happen then is if we took this rheostat now and we just increased the resistance, now the current would rise slower and slower and slower. And so what would happen is the firing angle would get later and later and later. Now, what is the latest firing angle that we can have with this circuit? Well, we only have resistance, and so that means that we cannot fire past 90 degrees. And so what that means is really, if we don't fire this by the time that we get to 90 degrees, we're not going to fire it because then the current's going to start going down. So how much resistance do we have to add to bring this firing angle up to 90 degrees exactly? So now, see, in this first part, we knew the resistance and we didn't know the firing angle. Now I'm asking you, I'm going to say, if we know that we want a firing angle of 90 degrees, how much resistance do I have to put in? And so what I'm going to do is I'm just going to erase this part right here, and I'm going to show you the calculation right here. I'm going to erase this part out of here, and now we're going to say I'm going to do the calculations now for 90 degrees. And the question is, how much resistance on the rheostat? Okay. So the rheostat right here, this 0 to 20 k ohm, how much resistance do we need to give us a 90 degree firing angle? Okay, let's look and see. So we know that at 90 degrees, our voltage will be 226.3 volts. Remember, that's like this, right? 226.3 volts. And so we go, well, what is the information that we have? Well, we know that at this exact point, if I don't have 80 milliamps, then I won't be able to fire. So I need to get exactly 80 milliamps at 90 degrees. So that means when I have 226.3 volts, I need 80 milliamps. Now here's the question. Is all of that 226.3 volts actually available to push current through the circuit into the gate? And the answer is no, because that 226.3 volts is applied from here to here, but there's a 3-volt drop across the gate. And so that means I have to go, okay, that means I have to subtract 3 volts of barrier voltage, barrier. And so what I have then is this, 223.3 volts, and I'm going to divide that by 0.08 of an amp. And that should tell me the total resistance. This should equal the total resistance of the trigger circuit. This equals R total of the trigger circuit. And let's calculate that out and see how much it is, okay? So we've got 223.3 volts divided by 0.08 amps, and that equals 2,791. 2,791 2,791 ohms. And so now if you take a look, you go, okay, this is the total amount of resistance I have to have in the circuit. I actually have two resistances. I have this one, and the total has to equal 2,791. This one is 1,000, so this one has to be adjusted or set to 1,791 ohms. And now between these two, I'll have this many ohms, and I'll get exactly a 90-degree firing angle. So that's how we calculate it. Actually kind of shows you the both variables. What do you do if you have the firing angle and you need to know the resistance? And the other one is, what happens if you know the resistance and you want to know the firing angle? So there's, we can work it both ways. All right. Now, this this is really dealing with the trigger circuit. And now what I want to show you, I'm going to show you a problem where we're going to work through it. I'm going to show you that how we need to kind of keep the two things separate, talking about the trigger circuit and talking about the load voltage, because it's kind of two separate parts of the circuit. And so we need to be aware that if we're dealing with the trigger circuit, we use the values in a certain way. And if we're dealing with the load circuit, well, then we need something different. Okay, so I'm gonna explain that in a little more detail almost right away here. So the circuit that I'm showing you here is it's a half wave rectifier. It's fed directly from AC, and what I really want to show you, I want to kind of show you in the circuit that there's kind of two specific areas here, and how to separate them in your mind so you don't get the values mixed up. So we're tied to an AC source. We can see that we just have one SCR. It's in series with the load, and this is the switch. Depending on when this fires, is going to determine how much of the waveform is cut away, and that will in turn determine how much load voltage there is. And this is just the trigger circuit, and it, of course, is going to determine when the firing angle occurs. So when we are dealing with this circuit down here, the trigger circuit, because the currents are very small in this circuit, every little bit of voltage is important. And so that's why we look at this and we say, the amount of voltage drop across the resistance, we're going to call that the resistance of the trigger circuit, the resistance basically, okay? It's the resistance part. And that's how we're going to actually determine the current. And we have to make sure that we subtract this barrier voltage of the diode, if it's used, and this barrier voltage from the gate to the cathode. Okay, those are going to be important numbers, and we need to realize if I have, a certain amount of voltage from here all the way across this, then I know that these barrier voltages have to come off before I deal with actually calculating the resistance, that we're going to have in this circuit. So that's an important part. And so then if we were to look at this other circuit, we go, well, here we have, and this is probably, this is quite common. It can be, up in the line voltages of 120 volts are very common for that. And so here we've got our AC line voltage, and we're going to have a load voltage that's probably at least 45 volts at its highest level, and then of course down to about 22.5 volts. If we adjust this so that it fires at 90 degrees, then we're going to be down to about 22.5 volts here, or say 45. Let me think about that. 54, it'd be 54 volts if we triggered at 0, and 27 volts if we triggered at 90 degrees. So this, remember, is a DC average voltage. So the point is what about this voltage? Now, the barrier voltage here, when we're talking about this load branch, we don't much concern ourselves with this voltage. It might be 1 or 2 volts, but it's not actually a large factor in what happens with the load voltage. It makes very little difference. Whereas down here, these barrier voltages will make a significant difference in how many ohms, for instance, we have in this circuit. And the reason that the voltage is more significant here is because it's such a small current. It makes bigger differences. So what I want to say is this. Whether you consider the barrier voltage across a diode is something that you need to look at the context, okay? So if we're talking about electronic circuits and you're looking at trigger circuits, for instance, or some other small circuit with low voltages and small currents, then you should count the barrier voltage across the diodes. But if we're talking about three-phase rectifiers fed from a 600-volt system, or even a half wave fed from a 208 120 system, the diode barrier voltages are going to be really, really insignificant compared to the line voltage and the total amount of power that we're calculating. So I just want you to be aware of that. Whether or not you count the barrier voltage is really a matter of context. So just kind of keep an eye on that, okay? So when it comes to this, what is it that we need? What are the sort of parts of the parts, the formulas and things that we need? What do we need to basically solve our trigger circuits? Well, we need to know this. We need to know the resistance, okay? Resistance values. We need to check barrier voltages. And so that includes a diode if we have one, and the gate voltage, okay? Barrier voltage. We need to consider gate current. Gate current is important. We need to be able to use our E instantaneous formula. E instantaneous, because we're going to use that depending on where the firing angles are, right? We're going to be looking for and calculating firing angles. Firing angles. And so we got our resistance, how much voltage we're applying here, barrier voltage drops, and these kind of things. Okay, these are all important in the trigger circuit. Now, when we come to the load circuit, pretty much what we're interested in is we want to know how much load voltage do we have, okay? Now this you can kind of stop worrying for a moment about the barrier voltage of the diode or the barrier voltage of the gate. You can kind of leave those things alone and you go, you know what, I just want to know what the E average is. And when it comes to E average, there's really just a couple or three factors, okay? So we've got E, and I'm going to call it E load, okay? This is the average voltage. In order to work with this E average, there's one piece of information that's vitally important, and it's the firing angle. Firing angle. So if you know the firing angle, and you know, what's the other thing you need to know? You need to know the peak voltage. So if you know the firing angle and the peak voltage of your AC supply, then you can figure out the load voltage. And where do you get the firing angle from? Well, you get that from basically you look at your trigger circuit and you say, okay, based on our trigger circuit, what kind of a firing angle do we have? And then you can go up here and say, okay, if that's the firing angle, I know my peak voltage is here, and I can just do a quick calculation using, in this case, my half wave formula. Half wave formula. And bang, there you go. You can get your load voltage at any firing angle, okay? And if this was if I had drawn this out as a full wave, supplying this AC would have come in and supplied a bridge, I would have basically exactly the same circuit, but with a bridge rectifier here, and this part of the circuit fed from the bridge rectifier. The only difference is you would do everything exactly the same, but you would use your full wave formula, right? So just remember, half wave is going to be half as much voltage as the full wave, but it's the same actual formula. So the next thing that I need to show you is we've up to now we've been talking about a resistance only triggering circuit, and that means that in the trigger circuit all we use is actually a resistor, okay, just a resistor, and and in this case, of course, we would have that gate protection diode, but essentially the idea is the only sort of component controlling the current really is resistance. And in a resistance only, I've blocked in, I've shown you this. If you look at one cycle of AC voltage, this is what the resistance only is capable of controlling. And it's only from 0 to 90 degrees. If you don't fire within that time period, then what you're going to see is, just an AC waveform. There'll be no load current whatsoever. You'll see across the SCR, you'll see just a whole AC waveform. It's like an open switch. Now, we're going to move to the RC circuit, trigger circuit. And in this one, what we're going to be able to do now is we're going to be able to control not only up to 90, but we're going to be able to control all the way from 0 to 180 degrees. And so that is going to mean that, see, what would have happened before this is if you would have turned the circuit on and started at 0 degrees, your load voltage would have started at the value of your line voltage times 0.45. And so as your triggering circuit got later and later and later and later, up to 90 degrees, you would have E line times 0.225, which is half of the 45. But immediately, as soon as you pass 90 degrees, the SCR would shut off. And then you would have 0 load volts. Now the difference here is that this one, in exactly the same circuit, in this exact same half wave, what would happen is you would start at 0 degrees, which would be a value of about E line times 0.45, right? And now you could go from that value and you would go all the way, you could trigger all the way until you got all the way to the end. So your voltage would get lower and lower and lower and lower until it faded out to 0 volts. And so this one here, you only have a little window of voltage control. This one, you can go from 45% of E line, which is your highest possible with a half wave rectifier, and you can fade that voltage all the way down to 0 volts. So RC circuits give you nicer, smoother control all the way to the end. This one would the voltage would go down, 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 and then bang, just shut off. Whereas this one is going to fade all the way down until it out at 0 volts, okay? So what we're gonna do is we are going to look at how to build this RC circuit. So I'm going to go ahead and draw the circuit, and then we're going to get started. So the circuit looks like this. So we start off from our AC supply. This again is going to be, I just have the SCR, it's connected right across the AC source. So that means it's going to be a half wave rectifier. But with this circuit, I will be able to control the firing angle all the way from 0 to 180 degrees. So let me show you how. Quite similar in a lot of ways, just a couple of little differences. I'd like to show it to you like this. So we apply voltage to the load and the SCR. Now remember, the SCR will block, so nothing's going past the anode until we get a trigger pulse. So to begin with, as we're waiting for the trigger pulse, this load voltage will be 0, and this will be the source voltage across the open SCR switch. So during that period of time, current will begin to flow through the circuit in this direction. Now realize we are talking about, I'm going to draw it in 2 colors here so we can see it. This is going to be this alternation. Okay, so I'm drawing you the current in green. This is what the current's going to do during this alternation. And then when we get to the other side, I'll draw it like this. I'll draw the current with blue. So to begin with, we've got current coming in. It will go through this resistor. And in order to fire the gate, what we need is we need for current to come this way, overcome this barrier voltage and this gate voltage here. And when all of that is in place, then we'll get our gate current. But guess what happens when the current comes down to this point and it goes, okay, there I have a path where I have to overcome some voltage to get current to go that way. But here I've got this great big spacious, it's like a big barrel that's empty. This capacitor is just an empty barrel. And so what happens is before any current will go this way, it goes, no, the first thing I got to do, because there's no opposition to it at all, is I have to fill the capacitor. So it starts filling the capacitor, okay? So the capacitor fills and fills and fills and fills, and now we get to 90 degrees. Now let me show you what would happen over here on a waveform so you can understand. Here's the AC waveform that is happening right now, okay? And here's the current that we have going in. Watch this. So we start and we've got current. And as the voltage is rising on our first alternation, the current is flowing into the capacitor. Okay, current's getting larger and larger. In other words, the rate that the current is flowing is rising higher and higher and higher. But here's the thing. What does it take to actually get a trigger pulse to flow into the gate? Well, we have to build up some voltage to shove it in. And some of you may remember that a capacitor, I'm going to show you a graph of how a capacitor charges. And your voltage and current look like this. Here's the capacitor, okay? And to begin with, at the instant you start charging a capacitor, this is I, the capacitor flows at its maximum level like this. And when you get almost to the end, like just to the point where it's full, all of a sudden the current goes like this and it drops off to nothing. And interestingly enough, think of voltage as like a pressure tank, okay? Or think about it this way. If you take a 2-liter Coke bottle, and you start pouring water into it, you know, at full blast, you've got the water stream going into the bottle and you're holding it. The water goes in, it's filling, 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 filling. Nothing much happens. But at the instant that it reaches the top, all of a sudden you have an explosion of water that hits you. So the pressure in the bottle doesn't occur until the bottle's full. And it's the same with a capacitor. A capacitor's voltage does not rise until just an instant before, basically as it's full. So what happens is this is the voltage. This is the voltage of the capacitor. It goes like this. Bang, like that. So this is E of the capacitor and this is I of the capacitor. So we're filling this capacitor. We're filling this capacitor, but the voltage is not going to rise until it's full. And if the voltage on the capacitor doesn't rise, then we're not going to shove any current into the gate. So this must fill up first before we're going to get that voltage fill that's going to shove current this way into the gate. So look at it like this then. Our current reached its highest point, but the capacitor is not full yet. And so what happens is now our current is still flowing in, even though the voltage is falling and the rate of current flow is slowing down, it is still filling the capacitor. So the capacitor and the resistor have to be sized together so that at a point where you're happy with it, we say, okay, at this point, let's say at this point right here, that is the point, and I would say right here, at that point, we go, okay, now the capacitor is full. And so what happens is as it fills, watch what happens. The voltage goes like that. And when that's full, all of a sudden the current coming this way goes bang. It's like deadheading against charge. And now the current goes like this, goes like this, overcomes that 0.7 of a volt, that 1.2 of a volt, and bang, it hits the gate and it fires the SCR. Now this could be all the way, you know, if we pour this current in slow enough, this could be all the way to 180 degrees. Looks like to me here, I've got about 150 degrees. That would be my estimate on this one, 150 degrees. 150 degrees. That's what that one looks like to me. So this is a really neat concept. You just have to think of this capacitor as a big barrel that you have to fill up. Now, I want to ask you this. If you had a trigger circuit and you checked it out and you could only get a firing angle of, let's say, 100 degrees, so just after here. You could only get up to 100, and then it would fire. So you go, huh, what can I do? Well, why don't we do this? You go, let's do this. Let's put another capacitor right here, like this. And now it's like having two barrels that you have to fill before you get enough voltage. So that just means that now we can delay it later. If you can go to 100 here, for sure, you can probably get now past 180. And what we want is we always want to be able to delay our firing angle all the way to this point, from this point. And so we need to make sure that we size the capacitors and the resistors in order to give us that delay. Now, just for your reference, when it comes to the resistance capacitance circuit, we're going to talk about it in terms of relationships. In other words, if I put in an additional capacitor, what's going to happen to the load voltage? And so we go, wait a second. Adding a capacitor means that I have more current that I have to fill up before I get my trigger pulse. So that means I'm going to have a later firing angle. So that means less load voltage. Okay, so that's the way we have to be able to think of it. It's just more and less kind of relationships. What happens if I introduce, I have just the same size capacitor, but I put the resistance, I dial the resistance to a lower value? Well, with less resistance, the current is going to flow faster and it's going to fill the capacitor quicker, which means I'm going to have an earlier firing angle, which means I'm going to have a higher load voltage. Okay, so these are the relationships that we need to have. Nobody's going to question you on the exact values, the RC constants, how we're going to figure that out. Okay, we're not going to do calculations on this RC trigger circuit. The resistance only, yes, we're going to do calculations. RC, no, we just want to look at it in terms of relationships so we understand how it works. Now, the nice thing about this circuit is this RC triggering circuit is that we can basically control a lot more control. And so remember, you can use this RC triggering circuit. You can use it in a half wave rectifier with the SCR, or you can use it in a full wave. And so the difference is that let me just show you the waveforms over here a little bit to the side. I think we've still got, see if we're still on screen here. Yeah. So let me show it to you like this. If you use resistance only, and I'll just show you one cycle. If it's half wave, we can just control this, right? But if it's full wave, we can control, in a full wave, we can control this, and this. Okay, that's resistance only. But if we go to RC, then if we have a half wave, we can control all of this. And if we have a full wave, we can control all of this. And so you see that the range of control with the RC is considerably greater. And so you can use either one, resistance or resistance capacitance, in either half wave or full wave. And the overall effect on voltage, of course, just remember, if you get into firing angles past 90, you just have to be careful with the math. You're going to wind up with some negative values for your sign and stuff like that. But basically, as you go past 90 degrees, the values of load voltage are going to get lower and lower and lower, right? And so I'm going to do some examples with you to show you that. But that's essentially the way it looks for the resistive capacitive triggering circuit. So the next the thing before we leave this diagram that I want to show you is so we've talked about how we're going to delay the firing angle, everything like that. But really, so far, I only talked about this first alternation, this positive alternation. And now we do need to talk about this negative alternation, and I'll show you why. Some of you are probably wondering, what is this component here for? Now, this is a diode, but I want to show you something that's important. Remember, at the instant that this is positive, if this is positive, then we have current coming in, going through the load, through the SCR, as soon as it fires, and this current comes in here. Now, what happens if this is positive, if this diode is made positive? Now you can see, and what I want you to take note of is that this diode is in reverse bias. It's installed reverse bias. And so that means that while current is coming in and charging the capacitor, this diode is blocking. Because if it wasn't, then it would be a short circuit, and the current would just go blowing in and probably blow the capacitor up. So we definitely need this to be reversed biased. Now, when we reach, and we've gone all the way through our circuit, we fired, we had our little bit of conduction, and then everything came down to zero. What you need to realize is this: when our charge builds up in our capacitor. So remember, this is building up against this plate. This is where all of our charge is built up, is against this plate. Now, when we actually fire the signal into the gate, some of this current goes into the gate, but not all of it. And so what that means is that at the total end of the alternation, we have now a capacitor sitting here with sometimes a fairly significant amount of charge on this plate. Now, I'm going to follow, and let's watch what happens over here. In our negative alternation, this becomes positive and this becomes negative. So now we're going to push this way. So we start pushing against the cathode of the SCR. Now the cathode is tough, and the anode to cathode reverse voltage, probably in the hundreds of volts, no issue whatsoever. It just says no. But the gate, not that strong, but it's got the gate protection diode to back it up, so it says no. So then what happens is, okay, now we can push this way. Now, we get down here and we've got some capacitors. Can current actually go through a capacitor? And the answer is no. There's no actual conduction through a capacitor. So what happens is, when this is pushing this way, what happens is there's an electrostatic force that pushes this current away from the plate. And so, that's the principle that capacitors work on. As the voltage here gets larger, it actually pushes this current away. Now, it could take a very long time for that current to bleed up through this resistor. And you want, before you get back to this point at the beginning of the positive alternation again, this thing has got to be empty. And so what you do is you provide this diode, and it's called a capacitor discharge diode. It's there for capacitor discharge. So now what happens? The voltage is pushing here. This charge goes, oh, great. Blam, back to the line, and it empties this. And so now this is empty. okay? Your barrels are empty again. Now your voltage falls back to 0. And here we go, and we're gonna start flowing current in again, and we want to get our same firing angle. Now let me just ask you this question. If we didn't have this capacitor here, and this was my first alternation, okay, where I got a firing angle over here, now went down, went through the negative, and I came back, and it's the second time now that I'm gonna try and get my firing angle. So imagine if there was already a bunch of charge here, okay? And I start trickling charge in through my resistor. It starts coming in. Now, because this is already half full, it would fill up very quickly. So the next alternation, maybe my firing angle would be back here. And then it might not, it might be early, or it might not even fire. It might miss an alternation. And so what happens is our phase control, our control of this alternation, all of a sudden gets all choppy and screwed up. And so very, very important that this diode is placed there. It allows this charge to disappear back to the other line, and it leaves this empty and ready for the next fill. And the next fill will start here. And as this rises, the current will flow in, filling, filling, filling. Get to 90, it's not full yet. Continue on, down, 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 and it will get to the exact same point. The voltage will shoot up at exactly the same time as it did in the previous positive alternation. So you'll get a constant firing angle. And so let me show you what the waveform should look like in this case. It should look like this. This is going to be, I'll show you by cycles, okay? There's 1, 2, I'll show you about 3 cycles just so you can get the idea. So this is going to, I'm going to put my 180 degrees on these, okay? So we're going to go like this. It's going to block, block, block. This will be the load, okay? Block, block, block. And then this is a half wave, so there'll be nothing there. Then it's going to block, 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 turn on, boom. Block that second alternation. Now it's going to block, 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 boom, turn on like that. And you want these to be nice and even, the same size all the time. And that's what this capacitor is for. Because if you don't, you'd get something that would look like this. It might block to there. And then maybe it would be like this. Maybe you'd actually miss one. You know what I'm saying? You'd get all this unevenness. And so what you want is you want them to be exactly the same all the time. And so what you want is this exactly. Just like that, okay? So that's the purpose of the capacitor discharge diode. And like I said, these capacitors, you know, several different capacitors are used in different circuits. So this one's very important that it is connected reverse biased. So if you go and you connect this up the other way, definitely going to have a circuit problem. And I want to summarize a little bit, and just to make sure we see where we're up to. We've been talking about the SCR, and the first sort of application was in a DC supply, with a DC supply. And in that case, we really had a solid state switch. Solid state switch. So you can review that if you need to. Just look back, take a little look back on the DC solid state switch. The next application that I would kind of say is, you know, it's a something identifiable sort of section, is the SCR used in an AC circuit, AC supply, and we created a single phase controllable half wave rectifier. Okay, and then the next application was really the same SCR with an AC supply, but put together with a bridge rectifier to actually feed into the SCR. And this gave us a single phase controllable full wave rectifier. Full wave rectifier. And now, just to kind of sum up, let's take a look at sort of how we can line this up. So in DC, basically this solid state switch, there were a lot of advantages to the solid state switch. When it comes to rectification, huge advantages to being able to control the amount of actual load voltage from this half wave rectifier. And remember, essentially, the formula for finding E average was equal to E peak times 1 plus the cosine of the firing angle divided by 2 pi, okay? And that gave you the load voltage. Then we moved on to the full wave. And the other little note that I'll make, because it was a little different between the two, was this one requires a gate protection diode, okay? A gate protection diode. Now this one here, remember we had the, we fed it, but we fed through a bridge, so that means it was actually DC going into the SCR. And this one, the formula, which is worth repeating, is E average is equal to E peak times 1 plus the cosine of the firing angle divided by simply pi. Okay, so as long as we have those firmly in mind, that kind of gives you a little bit of a summary of that. And remember, with this one, because we're feeding with DC, they're just ripples. It's DC, but it's fed from ripples, all of the positive alternations. We don't actually need a gate protection diode when we already fed it from a bridge. Okay, now what we need to do is continue on, and I have really just one more example that I want to show you of application of the SCR. And then that's pretty well it for the SCR. We'll have kind of gotten through the most important part of it. So what I'm going to do is I'm going to move this. And what I'm going to do is I'm going to show you the next application, the very next application. Now this is something that we call phase control. Phase control. And we're going to start with 1 SCR. And what I want to show you is if you take an AC waveform like this, because SCRs are unidirectional, in other words, one-way current only, that means that this SCR, number 1, can go right here. Number 1 SCR can literally control, if we were to use, particularly if we were to use RC, an RC trigger circuit, it would be able to control all the way from here to here. And we go, all this SCR ever does is block this alternation. And so, I started looking at it and they started saying, why don't we do this? Why don't we take a second SCR? So I'm going to call it the number 2 SCR. Okay, number 1 and number 2, so we need 2 of them. And we're going to hook this one up so that it can control this. Now, if you want to imagine what the circuit would look like, let me show it to you like this. Here's your line, and here's neutral, okay? So I'm going to come down like this. I'm going to say, we know that if I make this an SCR right here, and I make this the anode, and this the cathode, and this the gate, and I'm going to put the gate here. Sorry, this is the cathode. So anode, cathode, and gate, all right? Now, what's going to happen is when the AC is going positive, if this is positive, then it'll come down through here. And what I'm going to do is I'm going to run this over and up, and I'm going to call this the load. Okay, so this is going to be the load. Now, with just, and I'm not going to draw the trigger circuit, but I'm going to say, imagine that I wired this up with a trigger circuit. What I would do with this one SCR is I would only be able to control literally only up to here. Okay, I could only control as far as there. And that's if I use an RC trigger circuit, 0 to 180 degrees. So then we go, okay, what if I did this? What if I put another SCR here, but I hook this one up with the cathode here and the anode here, and I put it like this. There's my anode, cathode, and here's this gate, okay? So now I hook up in here, in this area. This is where my trigger circuits are going to be. So I have to have 2 trigger circuits. Trigger circuit is going to be in here handling the gates. And let's just look at the actual load and see what happens. As this is positive, so I'm going to show it to you like this. There's the negative alternation, and here's the positive alternation. So when this is positive and this is negative, what will happen is the current would flow down through the anode to cathode. Depending on when I trigger this, I could control this anywhere from here to here, right? So that would be fine. And then I would get, this would be like a DC load voltage. But now watch this. Now, when this becomes positive and this becomes negative, now I'm able to go like this. Comes like this, comes up, blocks against this cathode. Okay, this is SCR1, this is SCR2. Blocks against the cathode of SCR1, but goes through here and is now allowed to flow anode to cathode through this SCR and back into the line. So now SCR1 will handle this side and SCR2 will handle this side. And now we can go over here and we can conduct all the way through here. Okay, so now we're handling both alternations. One SCR does the positive, one SCR does the negative. Guess what? Each one of those SCRs is still only handling DC value, current in only one direction. But between the 2 of them, in this connection, which we call an inverse parallel connection. And in this inverse parallel connection, we can now control both alternations, and this is called full phase control. Now, where is this actually handy? Well, we can now use this in single phase or 3-phase circuits, and we can get waveforms. If we use RC triggering, let me show you the 2 extremes of waveform that we could see for the load. Okay, well, we could see this. If we trigger at 0 degrees with both SCRs, 0 degrees from the point that this one actually starts rising. So 0 degrees here. And then at that point, we ignore this one and we call this 0 degrees for this alternation. So we're triggering this one at 0, 180 degrees later, this one becomes triggered at 0. And what we do is we get a load for a waveform of voltage across the load that looks like this. Just like that. Now, what would happen if we triggered at 90 degrees, okay? This is 0 degrees. What would the load see if I triggered both SCRs, so one at 90, this one at 90, and then, it would conduct for the second half. Then this one would start its angle here, delay up until, for 90 degrees of that SCR's run, which in the cycle is actually 270, but it's 90 degrees for this SCR, trigger there. Well, it would look like this. The load would go like this: block, turn on at 90 degrees, conduct, block, turn on the other way at 90 degrees into that one, and there would be our voltage. Now, what is the average voltage of this waveform output? Is this an AC or DC load? Well, guess what? This is now an AC load because it has current going both directions, and the average voltage of this equals 0 volts. Anytime you have voltage, no matter what sort of shape it takes, if you have the same amount on one side as you have on the other side, this voltage cancels this voltage. And that's the old thing. In AC circuits, we say, what's the average voltage of an AC circuit? 0 volts. So what is the value we actually look for? We call it effective voltage. So if the effective voltage here of this waveform, if these were 170 volts, we know our effective or line voltage would be 120 volts. This one, if I go to 90 degrees, guess what my effective voltage would be? It's just going to be like quite a bit lower like that, right? Now, we're not going to do any calculations. I'm not going to ask you. There's no formula that I'm going to give you to calculate this out, but this one's pretty obvious. It's going to be about half the value that it would be up here, okay? So, but we now call this, we don't call it average voltage anymore. This is effective load voltage. And if we can control from 0 to 180 on both alternations, then we can vary this from our full line voltage all the way to 0 volts, okay? So lots and lots of control. Now, this method is used where you use two separate SCRs and you connect them together in this way, normally only on higher power loads. So loads that are, I think officially they say kind of about larger than 45 amps. So if you get into the hundreds of amps and you're doing full phase control, it'll be two separate SCRs connected together to give you this full phase control of an AC waveform. And so it's an interesting way of doing it. Now, what would happen if I had a three-phase circuit? And so I'm not going to go into too much detail, but I will show you this. A three-phase circuit would simply mean that I would have line A coming in, line B coming in, and line C coming in like this. And so I would basically split this like this, and I would have an SCR here, and this would be anode, cathode. And I'd have another SCR here, and this one would be cathode, anode. And I'd do the same thing here. This would be anode, cathode, SCR. This would be cathode, anode, SCR. And I'd have the same thing down here. Anode, cathode, the SCR is right here. Cathode, anode, SCR right there. These would join up here on this end. And I would now have three inverse parallel connections. And my line A would go like this, and this would be my motor, T1 over there. This would go over here to T2, and this would go over here to T3. Now, I know that I'm probably skipping ahead of you a little bit. You're going to be looking at this when you do motor controls. This is a very popular electronic reduced voltage starter. It's called a soft start. Okay, this is the soft start. And what a soft start does is it uses two SCRs per phase. It interlocks the gate, the gate signal. So each one of those SCRs will have a gate on it, and so there'll be some circuitry in there, some trigger circuitry that will make sure that whatever firing angle occurs in SCR1 will proportionally in time will happen the same in SCR2. And this one will do the same thing, and this one will do the same thing, but you got to realize this voltage is going to rise against these SCRs 120 degrees later, and this one 120 degrees later. So you're going to get your perfect 3 phases apart, but it's just that the voltage per phase will rise and fall depending on where your firing angle is. And so you can smoothly vary your output voltage of the soft start anywhere from 0 to 100% voltage. And that, of course, will be a very, very smooth way of operating, basically of starting this 3-phase motor. Okay, so we call this essentially 3-phase, full phase control. And it's, this starter is considered probably the smoothest, I guess. It would be the smoothest reduced voltage starter that there is. Okay, so at this point, we've kind of finished going through the SCRs, and the next thing that we're going to look at, we're really getting kind of close to the end of the SCRs, and actually all of the electronic components. We just have a little bit left with thyristors. So we've talked about, in that group we have SCRs, LASCRs, triacs, diacs, and UJTs. Now, what I'm going to do is we're going to wrap it up for this this particular session, but the next one we're going to take a look into the triac. We're going to look at the diac and the UJT, which are triggering devices, and I'm going to finish off showing you the LASCR. The LASCR is actually the component that is used in photocells for basically dusk to dawn lighting, things like that. Anything where you're sensing light and shutting things off, turning things on. So it's the LASCR. So that will be it for this one, and make sure you come back for the next one.